Good afternoon, and thank you for attending. I'll be presenting joint work with Gabi Nakibly from Rafael Research Center and Boneh from Stanford University. So let's start with a common simple scenario. Two people are having a conversation, they're talking, and near them on a table there is a smartphone device lying on the table. So we're asking ourselves, what can we do using the smartphone device? What information can we get using it? And can we possibly eavesdrop on the conversation? So let's assume we have some app running that actually requires no permissions at all, or possibly made the user somehow browse to some website that we can run some JavaScript on. So having that in mind, let's proceed with a couple of observations. The first one is that microphone access requires permissions, and it will be noticed by the user when those permissions are asked for. On the other hand, gyroscope access doesn't require any permissions currently. This is quite surprising. And actually, every application can access it without requiring the user's consent. Also, another observation is that MEMS gyroscopes, and there are two major vendors for it for the smartphone devices, they're susceptible to vibrations, in particular air vibrations, also known as sound. So we conducted a simple experiment. In this experiment, we played tones, different distinct tones near the smartphone device, and examine the spectrum. So we can see that we have significant corresponding peaks in those areas that correspond to these tones around 50 and 70 hertz. So this is a simple experiment, but it encouraged us to proceed and pursue further results. Okay, we also noticed some characteristics of those MEMS gyroscopes. So they can basically act as microphones. The sampling frequency available provided by the hardware is can differ according to the vendor and can be something like 800 hertz or even 8 kilohertz. And it is further limited by the operating system, by the driver, to something like 100 hertz on iOS, which is quite low, and somewhat higher rate on Android of 200 hertz. We also have a very low signal-to-noise ratio, which is adversarial to our attack. It's hard. Acoustic sensitivity threshold was noticed to be around 70 dB, and it basically corresponds to a loud conversation near the smartphone device. And because we have three different gyroscope axes, it is actually a directional microphone, as if we had an array of microphones. Okay. So we also noticed that browsers also allow gyroscope access without any notification. And for applications, we have the full rate provided by the OS of 200 hertz accessible. For browsers, for WebKit-based browsers like Chrome and Safari, we have a very low sampling rate available for access of around 20 hertz. This is very low. On the other hand, for Firefox, which is a Gecko-based browser, we have the full rate of 200 hertz accessible. So we can think about all kind of web-based attacks. For example, implanting some JavaScript in some website we managed to get the user to browse to, and then submitting those samples to further analysis to the attacker. The question raises now, how can we look into higher frequencies given we have this low sampling rate? So given the speech range is somewhat higher, there are a Nyquist range which is half of the sampling range, so it would be 100 hertz. How can we look into those frequencies that are from 100 hertz and above, like to 180 for adult males, even 255 hertz maximum for adult females? And it immediately raises the questions of whether the effect of aliasing is present in this case. Aliasing is folding of higher frequencies into the lower sub-Nyquist frequency range. It happens when you sample with low frequency without low-pass filtering the signal first. So do we have this filtering or do we not have it? And then we have those aliases. So we conducted an experiment in which we played tones between 120 and 160 hertz, which is above this Nyquist range. And we looked at the spectrogram. So we can see significant peaks, very noticeable peaks in the spectrum corresponding to those played tones. This was for a Nexus 7 device. So we actually do have for this device and all of Nexus devices, we have this effect of aliasing that allows us to capture higher frequencies. When we looked at the corresponding spectrogram for Galaxy, we saw much less noticeable peaks. So there we have some kind of low-pass filtering, which is bad for us. And we'll see it in the results later. From now on, this has encouraged us to proceed. We used the simple experimental setup, a room, simple speakers, and a smartphone. For the evaluation, we used the subset of TIDG speech recognition corpus. It is frequently used for evaluation of the speaker recognition, speech recognition algorithms. And we used a small subset, a relatively small subset of 220 total samples out of the 1,000 of samples in this corpus, containing different speakers and different words. We asked ourselves, what can we do with measurements obtained from a single device, from a single gyroscope? And we set 3 main tasks. The first one is gender identification, speaker identification, to tell which speaker is near the device now, who is speaking, and isolated word recognition, to take single separate words and to identify them. So just to test the waters, just to see what do we have in our hands and whether we can work, we have something to work with. At the beginning, we used an existing, tested, well-known speech recognition engine developed at the Carnegie Mellon University called Sphinx. So we used it for the isolated word recognition. We trained it with our samples recorded using the gyro and evaluated it on a test set. So we got 40% success rate, which is 14% accuracy, which is very low, but it's still somewhat better than the random guess. So we still have something to work with, and it's kind of encouraging. But we understood that we have to develop our own algorithms because the Sphinx is probably geared towards speech that is understandable to a human ear, whereas those gyroscope recorded signals, they're incomprehensible to a human. But you can possibly still train the classifier. So, okay, the preprocessing we did, we applied to our input was upsampling all our measurements, converted them to audio files in wave format, upsampled to 8 kilohertz, and performed automatic silence removal using voiced and unvoiced segment classification. This is very important because we don't want any noise to interfere with the recognition, any information that's not relevant to the pronounced word. We use the following features: Mel-Frequency Cepstral coefficients, MFCC. These are commonly used for audio processing and speech processing tasks. We use the delta MFCC, which are the derivatives, and tell some information about the temporal development of the features. And we've taken their statistical moments, like mean and variance. We also use the spectral centroid, which indicates the concentration of energy in specific frequency bands, the root mean square energy, and for incorporating the temporal information, we use the STFT, the short-time Fourier transform, which is basically a windowed spectrogram of the signal over time. We use the following classifiers: SVM, support vector machine, and multi-class SVM, which we constructed based on the binary SVMs. We used the Gaussian mixture model. This one is frequently used in state-of-the-art speaker identification and verification algorithms. And we also use dynamic type warping. So the dynamic time warping is particularly important for the isolated word recognition because it's good for comparing sequences, time series of features. So whereas an Euclidean metric, Euclidean distance wouldn't capture similarity between skewed and signals varying in time, but still representing the same data. You can pronounce a word more quickly and more slowly, smearing some part more than another. And the dynamic time warping find this optimal matching between the samples. So for the first task of gender identification, we use binary SVM, and we also use dynamic time warping with STFT features. Our best results for this case were 84% successful identification rate for an Nexus 4 device using dynamic time warping, and on Galaxy S3 we had 82% using SVM. Whereas the random guess probability, of course, because you have two possible groups, is 50%. So we see a significant advantage in recognizing the gender. So it indicates leakage of somewhat important information through this channel. We proceeded to speaker identification. In this case, we used multi-class SVM and GMM, and also dynamic time warping. The best results for this case are presented here, and the best results were actually 65% using dynamic time warping for a set of 5 male speakers. So the random guess probability here would be, of course, 20%. And for a mixed set of 10 speakers of female and male speakers, we had 50% identification. So this is a very significant advantage over random guess. We can see that a lot of information leaks. The most interesting, of course, is isolated word recognition. Can we actually identify speech? Can we understand what's being said in this conversation? So we've taken a limited dictionary of words, pronunciations of digits, including 2 possible pronunciations for 0 as O as well. The random guess probability is 9%, and the best result we got is for female speakers, 26% using dynamic time warping. This is also a significant advantage in guessing this kind of information. So for example, if something like a social security number, PIN code, credit card number is conveyed over the conversation, we have a significant advantage in guessing this information. If you look at the confusion matrix, you can see that many digits are confused with the digits 6 or 9. So for example, 2 can be by mistake identified as 6 or 9. So this is the source, apparently, of the kind of low percentage we got. But 6 or 9 specifically would be most of the time identified correctly. So we have significant advantage, especially for specific words. This is important. This is for speaker independent, which means there were different speakers pronouncing the words, which makes the task kind of harder. But for smartphone, it's of course very relevant to eavesdrop on a certain speaker, the usual user of this smartphone device. So the speaker dependent case would be very important. So for this case, we took a single speaker. We recorded the pronunciations of those words, and we trained our algorithm. And with the same algorithms, we got our best result was 65% correct identification of isolated words. And we can see on the confusion matrix that all of the samples are kind of on the main diagonal. There's quite low, quite little confusion and little false positives. So this is a very high percentage, actually. These are, I think, the important results in our study. I want to proceed to another scenario. So we were asking ourselves, what can we possibly do if we had more than one smartphone on the table? And they're collocated, they're simultaneously recorded in the same conversation. What can we do with it? Can we virtually obtain a virtually higher sampling rate using 2 devices? So we have two gyroscopes sampling. They're not synchronized. They're somewhat skewed. And can we possibly use those skewed samples to improve the recognition? So this setting is similar to the setting of time-interleaved analog data converters. In this setting, we have data converters. Each one samples the signal at somewhat low sampling frequency, but together, by combining their samples, you can reconstruct a higher frequency signal. So we have all kinds of challenges here. We can have an offset error, a DC offset error between them, for which we can compensate with the offset removal. We have gain error, normalization can compensate for that. And the hardest and the most important challenge here is the time skew. So while we don't want them to sample at the same time, because then we get more different samples that we can combine, we don't know precisely the time skew, the time offset between the samples, which is actually needed for a precise reconstruction of the signal. So we tested on simulations a non-uniform reconstruction algorithm, but that requires knowing those precise time skews and requires a subsample resolution, which we didn't have. So we had to set for a practical compromise. We used the expected value for those time skews, which is basically 50% of this sample period. And it corresponds to simple interleaving of the samples. So we take one sample from one gyro, take another sample from another gyro, and combine them to one vector. And this increases our feature vector. So we evaluated the simple approach and actually found that compared to the previous results for the speaker-dependent case using a single device, we have, for example, for the DT, dynamic time warping case, we have an increase of 12% in the performance. So 77% correct identification of isolated words using samples from two devices. So we have a significant improvement here. We suggest that using even more devices might improve the results even more. And perhaps somehow knowing the precise time skews and applying a proper non-uniform reconstruction scheme, which we didn't end up doing, might improve the results even more and perhaps even achieve some audible, comprehensible signal. Let's talk a bit about further attacks. So one possibility is using source separation. Because we have 3 axes and have actually a directional microphone, we can identify the number of speakers around the smartphone device and understand where the sound is coming from. And incorporating this knowledge, we possibly can improve the speech recognition. So the techniques for that are known. Another possibility is not related particularly to speech recognition, but it's a general audio processing task. So we're asking ourselves, can we infer from the measurements whether the device is in a room, in some outdoor settings, on a loud street? And of course, there's much more further research related to characterizing the physical properties of the gyros and how they respond to acoustic signals. I want to finish with some defenses, some suggestions for defenses. So first is software defenses, which can be low-pass filtering the raw samples provided by the driver, filtering out the higher frequencies, which convey so much information that is actually not needed for the applications. A 20 Hertz range, according to what WebKit provides, and apparently is enough for web applications, should do. And any access to higher sampling rate that an application might require should be noticed by the user and should require specific permissions. The hardware defenses could be some filtering in hardware of the sensor signals, which is not subject to configuration. We don't want something like the turning off the LED that was shown here to be available. And maybe applying some kind of acoustic masking to the gyroscope to prevent susceptibility to sound. I would like to conclude with the stating that giving applications direct access to hardware is always dangerous, especially in this case given the high sampling rate. we actually need to ask ourselves, do the applications need this kind of high sampling rate? And can we abstract the information from the sensor in some way? Thank you very much, and I'll take questions now.
Let's thank Jan. There were some AV challenges, so I'll leave time for a couple questions here.
Ulvar Erlingsson, Google. First question, did you just discover a better way to build directional microphones?
No, I don't believe it's a very good directional microphone. We didn't test it too much. Given the fact that you don't have more than one usual microphone, maybe you can use it, but I hope this kind of susceptibility will be prevented in future versions whatsoever. And
second question, so recent versions of Android have APIs that provide for sensor fusion and sort of automatic Kalman filtering and so on of the input signal. If that was the only API that was accessible, what applications do you envision would actually be precluded? What could software developers not do?
What could they not do? Can you clarify it a bit more?
So there are these high frequency sensor readings you can take out. If we precluded access to that, so the application developers could no longer see those, they could only see fused sensor readings from higher level APIs after Kalman filtering in particular. Would they lose some abilities?
I'm definitely not an expert on that, and after it got some publicity, there were all kind of comments that perhaps some applications maybe need a higher sampling rate. I don't believe that you need those measurements every 5 milliseconds. I guess a lot of applications could do with some abstractions like rotate left, rotate right, and that would do maybe for different applications. You would like the high sampling rate, but you definitely need to ask for specific permissions, to include it in the permissions list during the installation, or to pop up something that the user will notice and be conscious of.
Okay, one more.
Bill Soley from Apple. So the gyroscope is sensitive to angular movement. Have you looked at also the accelerometers? I looked a bit at the accelerometers. I trusted some research. So this is not a new fact by itself that gyroscopes are susceptible to acoustic noise in general. The speech recognition is the new surprising thing. But some previous studies indicated that the gyros are more susceptible to acoustic noise. That's why we focused on them. Thank you.
Let's thank all of our speakers in the session.